Welcome to Learning Outcome 2, where we look at what controls how fast a reaction goes. We'll cover collision theory, the 5 main factors that change the rate, and the Maxwell-Boltzmann distribution that ties it all together. Over this outcome, we'll define what we actually mean by the rate of a reaction and how to measure it in the lab. Then we'll meet collision theory and the idea of an effective collision, run through the 5 factors that speed a reaction up or slow it down, see how each is explained by collision theory, and finish with the Maxwell-Boltzmann distribution and how temperature and catalysts shift it. So, what is reaction rate? Put simply, it's how quickly reactants get used up or products are formed, measured as a change in amount per unit time. Usually, we track it as the change in concentration, divided by the time taken, in units of moles per cubic decimeter per second, or sometimes cubic centimeters per second for a gas. And here's a pattern worth remembering. The rate is nearly always fastest right at the start, and then slows down, because the reactant concentration keeps falling as it's consumed. To measure a rate, we follow some property that changes as the reaction goes. We might collect a gas in a gas syringe and track its volume over time, or watch the mass drop on a balance as gas escapes, or follow a color change with a colorimeter. A classic one is timing how long a cross takes to disappear as a sulfur precipitate forms in the reaction of sodium thiosulfate with hydrochloric acid, which gives sodium chloride, sulfur, sulfur dioxide, and water. Let's do a quick calculation. Say 48 cubic centimeters of gas is collected in 40 seconds, and we want the average rate. Rate is just the volume of gas divided by the time, so that's 48 divided by 40, which comes to 1.2 cubic centimeters per second. Nice and straightforward. A few terms to lock in. The reaction rate is the change in amount of reactant or product per unit time. Collision theory is the idea that particles have to collide before they can react. An effective collision is one that actually leads to a reaction because it has enough energy and the correct orientation. And the activation energy, EA, is the minimum energy those colliding particles need for the reaction to happen. Collision theory is the heart of all of this. Before anything can react, particles have to collide, but not every collision does the job. For a collision to be effective, 2 things must be true. The particles need energy at least equal to the activation energy, and they have to hit with the correct orientation. The more effective collisions you get each second, the faster the reaction goes. Let's unpack those 2 conditions. First, energy. Bonds have to be broken before new ones can form, so only particles arriving with energy above the activation energy can react, while low-energy collisions just bounce apart unchanged. Second, orientation. The reactive parts of the molecules have to line up properly, and even a high-energy collision fails if the alignment is wrong. Both conditions have to be met together for a reaction to occur. There are 5 factors we can change to alter a reaction's rate: the concentration of dissolved reactants, the pressure of any gaseous reactants, the temperature of the mixture, the particle size or surface area of a solid, and the presence of a catalyst. What links them all is that each one changes either the frequency or the energy of the collisions. Take concentration first. A higher concentration means more particles packed into the same volume, so on average, they're closer together and collisions happen more often. More collisions each second means more effective collisions, so the rate goes up. You can see it clearly comparing dilute and concentrated hydrochloric acid reacting with magnesium ribbon, which gives magnesium chloride and hydrogen. Pressure works in a very similar way, but only for gases. Squeezing a gas into a smaller space pushes the particles closer together, which raises their concentration, so they collide more frequently and the rate rises. It only applies where gases are involved. Of course, take the Haber reaction, nitrogen plus hydrogen in equilibrium with ammonia, run at high pressure. In fact, raising the pressure of a gas is really the same idea as raising the concentration of a solution. Let's put those two together. Concentration applies to dissolved reactants. More particles per unit volume, sitting closer, colliding more often. So doubling the concentration roughly doubles the collisions. Pressure applies to gases only. A smaller volume packs the particles closer in exactly the same way. Same underlying cause, just one for solutions and one for gases. Temperature is a particularly powerful factor. Heating the mixture gives the particles more kinetic energy, so they move faster and collide more often. But the real story is energy. Many more of those collisions now exceed the activation energy, so a much larger fraction are effective. That's why even a small rise in temperature can produce a big jump in rate, and the energy effect matters far more than the simple speed effect. Now, particle size and surface area, which matters for solids. Only the particles right at the surface of a solid can react, so if you break that solid into smaller pieces, you expose far more surface. A powder has hugely more surface area than a single lump of the same mass, so there are many more particles available to collide, and the rate climbs. That's why powdered calcium carbonate reacts much faster with acid than marble chips do, giving calcium chloride, water, and carbon dioxide. The fifth factor is a catalyst. A catalyst speeds a reaction up without being used up itself, and it does that by offering an alternative pathway with a lower activation energy. With a lower barrier, more of the particles now have enough energy to react, so more collisions are effective and the rate increases. A good example is manganese dioxide catalyzing the decomposition of hydrogen peroxide into water and oxygen. And at the end, the catalyst is chemically unchanged. Let's reason one through with collision theory. Marble chips react slowly with acid, so why does crushing them into a powder speed things up? Only the particles at the solid surface can meet the acid, and crushing exposes far more of those calcium carbonate particles, greatly increasing the surface area for the same mass. The acid now collides with the solid much more frequently, so the number of effective collisions each second goes up, and the rate rises. Here's another. A reaction takes 60 seconds with acid at 1 mole per cubic decimeter, and we double it to 2. Doubling the concentration doubles the number of acid particles in each unit of volume, so they're twice as crowded, and the collision frequency roughly doubles. That means about twice as many effective collisions every second, so the rate roughly doubles and the time taken roughly halves, dropping to somewhere near 30 seconds. Quick check. What two conditions have to be met for a collision to be effective? Why does increasing pressure only matter for reactions involving gases? Can you list all 5 factors that affect rate? And why does a powder react faster than a single lump of the same solid? Have a think. Now for the Maxwell-Boltzmann distribution, which shows how energy is spread among the particles. In any sample, the particles have a whole range of energies, and this curve tells us how many particles have each energy. No particle has 0 energy, so the curve starts at the origin, then rises to a peak and falls away with a long tail to the right. The peak marks the most probable energy, and the total area under the curve represents the total number of particles. Let's read the curve carefully. The x-axis is the kinetic energy of the particles, and the y-axis is the number of particles with that energy. We mark the activation energy on the x-axis, and only the particles to the right of it, in the shaded tail, have enough energy to react. The important thing to notice is that most particles actually have less energy than the activation energy, which is why not every collision succeeds. So what happens when we heat the sample? The total number of particles doesn't change, but the peak of the curve gets lower and shifts to the right, and the whole distribution flattens and spreads towards higher energies. Crucially, that means many more particles now have energy above the activation energy, so the shaded area beyond it grows noticeably larger. A bigger fraction of collisions is effective, and the rate goes up. Comparing the two temperatures side by side helps. At the lower temperature, the curve has a higher, narrower peak sitting at a lower energy, with only a small area beyond the activation energy, so few particles make the grade. At the higher temperature, the peak is lower and broader and has moved to higher energy, and the area beyond the activation energy is much larger, so many more particles exceed it. That growing shaded area is the whole reason the rate rises. Let's use the distribution to explain a real rate change, going from 25 to 35 degrees Celsius. At the higher temperature, the whole curve spreads to the right, and its peak drops and moves to higher energy. The number of particles with energy above the activation energy increases, so the area under the curve beyond that point grows. More collisions now clear the activation energy, so the proportion of effective collisions rises sharply, and that's why the rate increases with temperature. A catalyst affects the same picture, but in a different way. It doesn't change the shape of the curve at all, because the temperature and the number of particles stay the same. Instead, it lowers the activation energy, so the line marking it slides to the left on the same curve. That instantly puts a larger fraction of particles beyond the activation energy, so more collisions are effective and the rate goes up. It's worth linking this to the enthalpy profile, which plots energy against the progress of the reaction. The reactants have to climb an energy barrier to react, and the height of that barrier is the activation energy. A catalyst provides a new pathway with a lower barrier, so it's easier to get over. But note that the overall enthalpy change, delta H, is completely unchanged. Only the activation energy is reduced. Let's gather a few more terms. The Maxwell-Boltzmann distribution is the curve showing the spread of molecular energies in a sample. The most probable energy is simply the energy at the peak of that curve. A catalyst is a substance that speeds a reaction up by lowering the activation energy and isn't used up. And an enthalpy profile is a diagram of the energy change along the reaction pathway. Last check for this outcome. On the distribution, which particles are actually able to react? Can you describe two ways the curve changes when the temperature rises? How does a catalyst change the position of the activation energy line? And does a catalyst change the value of delta H, and why? Give those a go before moving on.